Good morning, good afternoon, good day from Vienna here in Austria. My name is Gerard Graham. I'll be the convener today for our invited talks on the Anthropocene. And with me on my left is my colleague, Martin Kalinowski. So we're looking forward to the two presenters that have joined us today, Professor Helmut Grassel and Dr. Colin Waters. So why are we here on this particular topic? I think we're all aware that it's become globally a topic of interest, that the Anthropocene, although not a formally defined geological epoch, it's created a lot of interest and debate about the need to recognize a new geological age that is defined as having been profoundly influenced by mankind. In order to be accepted, the Anthropocene would have to be clearly visible over geological timescales within the strata, of course, that are currently being formed. Its boundary could be set by changes in geological processes such as urbanization, global warming, or agricultural impact on erosion, for instance. The long-lived stratigraphic indicators, such as anthropogenic pollutants, would include microplastics or proxies for elevated atmospheric carbon dioxide and radioactive isotopes from nuclear testing. These are amongst a wide range of indicators that's currently under consideration. In fact, the first nuclear test conducted on the 16th of July 1945 is proposed as marking the beginning of the Anthropocene. So, as I said at the beginning, we have two presenters with us, and our first presenter is Professor Helmut Grassel. He is the former director at the Max Planck Institute for Meteorology in Hamburg and also emeritus professor for general meteorology at the University of Hamburg. He was director of the World Climate Research Program at the WMO organization in Geneva. He's a two-time member and chairman of the German Advisory Board on Global Change. He's a winner of the German Environmental Prize for his contribution to the explanation and prediction of climate fluctuations and chairman of the board of the Federation of German Scientists. Professor Grassel received the Reinhard Suring Plaque for outstanding scientific and organizational services during his active time as head of the Max Planck Institute for Meteorology. He's known for his commitment to incorporate the findings of current climate research into political decision-making processes, as well as his ability to explain them to the general public. So, welcome, Professor Grassel. If you could please take the floor now and start sharing your slides with us.
Welcome to my presentation. I was asked by Martin Kalinowski to talk about Paul Crutzen's contribution to the understanding of the Anthropocene. Paul Crutzen deceased earlier this year, and he was my friend over decades. And when I once met him in Mainz, where he was the director of the Max Planck Institute for Chemistry, he said to me, should I start talking about geoengineering? Because the threat of climate change is so large that maybe we should use geoengineering as the last rescuing action. But here I will start by showing not only his photograph, but the short first part of a paper in Nature, which he published in 2002, and I read it because it is maybe the first fully accepted by the public of the word Anthropocene. He wrote, "For the past 3 centuries, the effects of humans on the global environment have escalated. Because of these anthropogenic emissions of carbon dioxide, global climate may depart significantly from natural behavior for many millennia to come." At this time, this was not standard to talk about many millennia. Now we know, and the next IPCC report will talk about it. It seems appropriate to assign the term Anthropocene to the present, in many ways human-dominated geological epoch, supplementing the Holocene, the warm period of the past 10 to 12 millennia. The Anthropocene could be said to have started in the latter part of the 18th century, when analysis of air trapped in polar ice showed the beginning of growing global concentrations of carbon dioxide and methane. This date also happens to coincide with James Watt's design of the steam engine in 1784. In the next slide, I will talk about the present. Yeah.
Hartmut, we don't see your slides yet. Just try again to share them.
Yes, I can. Can't you see?
Not yet.
Not yet.
Yes.
Moment, please.
And it's
Below the PowerPoint on your screen, there.
Yes.
Share.
Excuse me.
On your screen at the bottom, you would see the share button. Yes. Right at the lower end of the screen, there should be several buttons. One of them would show share.
Yeah, but I can't see them at present. That's why they have disappeared. Excuse me. Now I have them again. Excuse me.
No problem. We'll tell you the moment we can see the slides.
You can see.
Not yet.
Not yet.
There is the share button. It's to click and see the
So, Hartmut, let's see if we. So on your screen, you will see in WebEx, you will see the share button. When you click that, it will give you windows that you can select, and then you select a PowerPoint to share. You click on the PowerPoint screen to share.
I have pushed the button.
Now it's come up. It's not quite in the center, but if you go to yes, that's it.
So it works now.
Now we can see the slide.
Thank you for helping me. I will continue by representing the present situation. We scientists, we are more and more powerful. Based on technological and societal progress, a higher percentage of humans than ever before enjoys a decent life and lives on average much longer than all earlier generations. But at the same time, the misuse of research results also has led to a major and a big growing threat to weapons of mass destruction. Maybe, however, this has reduced the number of conventional wars. Nobody knows really. Research on the functioning of the Earth system, predominantly in democratic countries, has on the other side unveiled threats caused by the mere overuse of resources. This overuse has driven us outside several boundaries into which we have to come back. Paul Joseph Crutzen, a Dutchman and a civil engineer by training, is among those having laid the foundation for the understanding of the transition or the transgression into the dangerous zone and the way back into a safe one. I will talk about not only the term Anthropocene, but when did it start? In parts I already answered. I will talk about the stratospheric ozone layer, the so-called ozone hole, the Montreal Protocol, nitrous oxide increase, continuing to weaken the ozone layer, aerosol particles in the stratosphere, both for geoengineering and nuclear winter, from nuclear winter, and finally, the extreme sensitivity of sea level to temperature changes in the atmosphere. Paul Crutzen published jointly with Eugene Stürmer already in May 2000 in the IGBP newsletter a definition of the Anthropocene. He said, or both authors said, considering these and many other major and still growing human activities on Earth and atmosphere, it seems to us more than appropriate to emphasize the influence of mankind in geology and ecology by proposing to use the term Anthropocene for the current geological epoch. And he really published it in an article in Nature in 2002, from which I have taken part of the definition in my first slide. There is a debate depending on where you come from. If you are, like Paul Crutzen, a person dealing with the chemistry of the atmosphere, it is clear that the changed chemical composition of the atmosphere is the start of the Anthropocene, if it is anthropogenic. You in the group which is which has the main saying in this conference, for you the Trinity test of 6 July 1945 in New Mexico, USA, may be the starting point for the Anthropocene. Well, it is not so important what is the dominant starting point. The reality is that we are a geological force, we, the Homo sapiens, on this planet. In my next slide, I come to his fundamental, to Paul Crutzen's fundamental detection of the reason for the comparably low ozone values in the stratosphere. He was the first to find the so-called catalytical cycles, where a certain compound attacks an ozone molecule, but at the end of the chemical reactions, it comes back undisturbed. So these are molecules like NO who can destroy if they are not removed from the atmospheric layers in which they existed at the beginning. If they are not removed from there, they can destroy thousands of ozone molecules by a single other molecule. And this was the reason to give Paul Crutzen as the first and until now only scientists getting a Nobel Prize because of environmental research. He was the scientist to take the next fundamental step, it was cited now by me from the Nobel Prize Committee of the Swedish Academy of Sciences in 1995. In 1970, he showed that the nitrogen oxides react catalytically, as I already said. And so they accelerate the rate of reduction of the ozone concentration in the stratosphere. As I said earlier, this was my error. I have to go forward. The Nobel Prize, the Nobel Committee press release in 1995 continues by saying, these nitrogen oxides are formed in the atmosphere as a consequence of the chemically stable nitrous oxide, which originates from the soils, so from microbial transformations in the ground. Or in other words, a farmer using nitrogen fertilizers creates, because a few percent of the nitrogen fertilizers are transformed into nitrous oxides, he creates a molecule which survives in the atmosphere about more than 100 years and is only destroyed in the upper stratosphere, where ultraviolet radiation is strong enough to create from N2O also NO molecules. So it is Paul Crutzen's main achievement to show that action by all farmers in this world is, if it is increasing, an attack to the stratospheric ozone layer. Now we know better than when Paul first time pointed to the NO or NOx compounds. Now we know that chlorine compounds and also molecules derived from water vapor are responsible for the comparably low ozone concentration values in the stratosphere. And it is quite interesting to see that Paul Crutzen's detection of these catalytical cycles came only 15 years before other scientists detected the so-called ozone holes, which was an attack of chlorine compounds or bromine compounds in the upper stratosphere and in the lower part of the stratosphere at clouds, as so-called stratospheric clouds. It was an attack to the ozone layer, which fortunately showed up first in an area where nobody lives, except for a few scientists. So the ozone hole over the Antarctic is, as I say in German, ein Zeichen Gottes. And this was Paul's achievement as well. He was able to convince in an enquete commission of the German parliament, where we both, Paul and I, were members, to convince our politicians to strengthen the ozone at the Montreal Protocol, which was signed in 1987, and which we in 1989 and 1990 asked to be strengthened. And Paul Crutzen was not only the person detecting the catalytic ozone destruction, but also his finding was a key for the understanding of the ozone hole, and he contributed as well to the research on the ozone hole. Now we have, and this is always an important point for us scientists, are we able to convince the decision makers to do something about the threat detected? We have now international law that has to bring us back into the safe zone. If you look to literature, you will find that we have transgressed into the unsafe zone for the nitrogen cycle, for the carbon cycle, for the phosphorus cycle, and we have transgressed into a dangerous area concerning the loss of biodiversity. For some of these threats, we do have international law now. The success story is clearly the Montreal Protocol, which I mentioned before. And we have a goal set in the Paris Agreement from 2016. Since the 6th of November 2016, it is a binding protocol to the United Nations Framework Convention on Climate Change. So we have a goal set. And as you may have heard, in Germany, we had a ruling of our highest court concerning the Paris Agreement that our government's laws are putting too much pressure on the young generation. And now we have a reduced time span to become climate neutral in Germany. It was set from 2050 to 2045 in the recent few days. Another point which Paul Crutzen was the key person to point to was the impact of the rise in atmospheric nitrous oxide on stratospheric ozone. I take here from Rolf Müller from the next AMBIO issue, the 50th from this year, that already Paul Crutzen and Peter Ehalt in 1977, when they both were working at the National Center for Atmospheric Research in USA, pointed to what later on became the threat to the continuing threat to the ozone layer caused by fertilization with nitrogen compounds at the surface. And I have in parts already said what is written here in the lower portion of my diagram. Another point where Paul Crutzen was fundamental was the threat to human beings at the surface through aerosol particles in the stratosphere. It was in 1982 where he published first time a paper on the nuclear winter, jointly with a colleague. And he was also the first high-ranked scientist with a Nobel Prize daring to talk about geoengineering. And he, in 2008, talked about sulfate particles in the stratosphere to cool the Earth's surface. Before it was published, he asked me whether he should submit this paper. I said to him, yes, you should, because his high profile allowed to start massive research on the understanding of aerosol particles in the stratosphere. And it was tied, in this case, to the sulfur injections into the stratosphere, where these sulfur compounds are transformed into particles. Now, excuse me, the result of many research papers and technological progress in the renewable energy excuse me, I have to go back. Now, the result of many research papers and technological progress in the renewable energy sources arena is emission reduction is the only way without new risks. But he, at the beginning, when he asked me, should I submit it, said, all I want is to stimulate a massive research. And this was done, and now we have a solution. Very recently, he talked to me and said, yes, it was good to have this paper, but he was, as a scientist, also accused by many. Why have you talked about albedo enhancement through sulfur injections? So it was, yeah, I would say, if you have a Nobel Prize, you are allowed to be, again, outside the mainstream for some time, and the people will accept easier than from another young person not having this high profile. At the end of his life, not directly at the end, but when he was already a retired director of the Max Planck Institute for Chemistry in Mainz, he was asked by a journalist from Nature, aside from as a Nobel laureate, how do you want to be remembered? And he said, as a person who significantly contributed to the understanding the processes that determine the distribution of ozone in the atmosphere, and as the scientist who coined the term Anthropocene, a new geological epoch dominated by anthropogenic activities. And one of the scientists who drew attention to the devastating climate consequences of a nuclear war, the so-called nuclear winter. More people would die of the indirect consequences of mass starvation and disease than would be killed by the nuclear bombs. This was my presentation in honor of Paul Crutzen, who as a single person was largely responsible for international law. Isn't it a wonderful achievement of a scientist that his findings lead to international law within his lifetime? Thank you for listening.
Thank you very much, Hartmut. I want to remind our participants that you can use the chat to raise any questions. You can do it now or at the end of the session. We will take general questions. And of course, with opening of the session, you can continue to also put your questions in here, and it can be answered in the chat room by the presenters. Let me just see. Anything? No questions yet. So I think Hartmut, thank you very much for this presentation, and we will continue with the next presentation, and at the end see if there are questions for both of you and Colin Waters. So the next presentation is on the artificial radionuclide fallout, a marker for the start of the Anthropocene by Colin Waters. Colin is a retired principal mapping geologist, formerly of the British Geological Survey, with specific interest in Carboniferous and Anthropocene stratigraphy. He's an honorary professor at the Geography, Geology and Environmental School of the University of Leicester. And in 2019, he was visiting professor at the University of Vienna. He's been secretary of the Anthropocene Working Group of the International Subcommission on Quaternary Stratigraphy from 2011, and its chair since 2020. Colin has been secretary of the Stratigraphy Commission of the Geological Society of London since 2006. He has 144 peer-reviewed publications. So Colin's presentation is pre-recorded. If we could start that now, thank you.
Thank you for the invitation to talk on the topic of the Anthropocene as a potential new geological epoch, and particularly how artificial radionuclide fallout may have an important part in the definition of this term. I'm speaking as the chair of the Anthropocene Working Group of the International Subcommission on Quaternary Stratigraphy, the international body tasked to assess this concept as a potential addition to the geological timescale. The first part of the presentation will explore the diverse evidence for the Anthropocene to be defined as a geological epoch. The second part will then concentrate on describing the importance of nuclear fallout to resolving the timing of the Anthropocene, in particular covering key events related to artificial radionuclide distribution, suitability of different isotopes as a marker for the Anthropocene, the scale of atmospheric nuclear testing, to consider variations in radiocarbon and plutonium signals in different environments, and then to briefly describe our current investigations. Geologists read the history of our planet through layer by layer of strata, like reading pages of a book. And the history that we have determined is one of 4.6 billion years of an evolving planet, which at times has witnessed significant global change, perhaps the most prominent of which are the 5 mass extinction events, marked by red lines, the last of which saw the demise of the non-avian dinosaurs and about 75% of all species 66 million years ago. To express the evolving nature of the planet, geologists have formulated the geological timescale, which includes named time units, which help label distinctive phases in Earth history. Officially, we live in the Holocene, which represents the last 11,700 years since the end of the last ice age, but there is growing evidence that this interval of relative stability in the Earth's system has been succeeded by a new epoch, the Anthropocene. So how do we formalize a new geological time unit? It is useful to look at this example from deep time to explain the approach. The base of the Silurian is defined at what is known as a Global Boundary Stratotype Section and Point, or a GSSP, or Golden Spike, at a specific location, here in southern Scotland, representing a type reference section. The end Ordovician was a time of major glaciation, and as seen in the previous slide, one of the 5 mass extinction events. Irrespective of these major but slow and diaphanous changes to the Earth system, the start of the Silurian is defined by the first appearance of a fossil graptolite, Echinograptus ascensus, in this section, not because it was an Earth-changing event, but because of the practical ability to widely correlate the appearance of this widely distributed marine species across the globe. This is relevant to discussions later on the use of radionuclides in the Anthropocene. The concept of the Anthropocene has evolved significantly since being originally formulated by Paul Crutzen in 2000. Our website provides a brief definition based upon our ongoing research. So the Anthropocene denotes the present geological time interval in which many conditions and processes on Earth are profoundly altered by human impact. This impact has intensified significantly since the onset of industrialization, taking us out of the Earth system state typical of the Holocene epoch that postdates the last glaciation. Its beginning would be optimally placed in the mid-20th century, coinciding with the array of geological proxy signals preserved within recently accumulated strata and resulting from the great acceleration of population growth, industrialization, and globalization. In the next few slides, I will give some examples of these geological proxy signals, which can be subdivided into 4 categories, relating to the appearance and rapid dispersal of many new mineral forms, including metals, plastics, and industrial fly ash, rock types, including concrete, and sediment bodies, including artificial ground, together with sediments released by land use changes. Biological evidence, including the consequences of extinctions, geologically unprecedented species invasions, and marked changes related to domestication of species. Recent climate change and rising sea level trends that are outside the Holocene trajectory, and chemical signals which include isotope patterns altered by perturbations to the carbon and nitrogen cycles, disseminated metal and persistent organic pollutants, and artificial radionuclide traces, many of which are novel signatures. The number of mineral species on the planet has increased slowly over the last 4.5 billion years, from a few dozen to about 5,000. Humans may be considered to be responsible for the latest surge in mineral species. The International Mineralogical Society don't catalogue these as minerals, which have to be naturally forming, but the number of novel mineral-like compounds is now in excess of 200,000. Many of these were developed and have become used since the mid-20th century, though there is no systematic analysis. Just one example is tungsten carbide, a novel compound used in hundreds of billions of ballpoint pens since 1961. Plastic polymers were rare before 1945, but by 2016 account for 380 million tons of production per annum, and by 2050 the anticipated production is 1,800 million tons. Annual production currently exceeds the weight of all 7.5 billion humans on the planet, and the cumulative production since 1950 could produce a plastic wrap to encircle the planet nearly twice. And microplastics are now found throughout the oceans, accumulating in modern sediments in even the deepest ocean trenches. The growing scale of global artificial deposits shows the familiar upturn from the 1950s. The graph shows the annual mineral and metal production figures alongside estimates of typical overburden or waste, shown as the pale blue curve, with coal presented separately in orange, as it is by far and away the greatest mass of minerals extracted from the ground. It also includes data on cement and aggregate production in grey, primarily as a source of concrete, the most extensive artificial rock on the planet. Along with estimates of offshore dredging figures, shown in yellow, and civil engineering earthworks in dark blue, the sum in 2014 was estimated at 316 billion tons of sediment, or 150 cubic kilometers of materials moved by human activity in 1 year, equivalent to about 43 tons per person on the planet. To truly realize that human activity is a significant geological force, consider that by comparison, all rivers on the planet shift only 16 billion tons of sediment to the oceans in 1 year. Humans have significantly perturbed river systems through construction of dams, with 58,519 large dams having been built by 2017. 89% of this number were constructed after 1950 at an average rate of 2 per day. The resultant impounding of some 3 trillion tons of sediment within reservoirs has led to a reduced flux of sediments to the oceans by about 15% compared with pre-human levels. This is in fact even more significant in that it has dramatically reversed a trend of much increased sediment flux due to the expansion of agriculture and deforestation. This has significant impact on many of the world's deltas, which through starvation and sediment supply are subsiding at a time of rising sea levels. Humans are believed to have long influenced biodiversity, causing extinctions of large mammal species following migration into Australia and especially into North America 13 to 11,000 years ago. In a short time during the Anthropocene, the number of extinctions of terrestrial vertebrates has escalated, and although until recently defaunation has been less severe in the oceans than on land, our effects on marine animals are increasing in pace and impact. I mentioned earlier that geologists often use changing fossil types as a means of characterizing the definition of geological time units. It is estimated that some 338 vertebrate species have become extinct since the 1500s, which may not sound many, but current extinctions of species are typically up to 1% over the last 500 years, which is considerably higher than the rate of the last million years, and for snails and clams are considerably higher still. But when one considers threatened species, such as those on the IUCN Red List, magnitudes are creeping towards the 75% threshold for a global mass extinction event. As a consequence, it is being suggested that we are on the trajectory towards the 6th mass extinction event within the next couple of centuries. Perhaps what is more apparent over recent decades is the scale of declines in population abundance of thousands of mammals, birds, fish, reptiles and amphibians around the world, as demonstrated in the WWF Living Planet Index shown here. The declines between 1970 and 2014 are especially pronounced in the 3 tropical realms, with respectively 89%, 56% and 64% of declines in populations in the Neotropical, Afrotropical and Indo-Pacific realms, with a global decrease of 60% on average. The Anthropocene has also seen a vast increase in the movement of species both intentionally and accidentally around the planet. An example of the latter is the invasive marine species that are transported in ballast water or by biofouling on ships' hulls. This figure shows the extent to which hotspots of invasive marine species are largely constrained by modern global marine trade routes, resulting in more than 250 new species appearing in the Mediterranean Sea. Human impact on the biosphere also includes a significant reduction in biomass of wild land and marine mammals over 100,000 years, which is now some 6 times lower. But we've also caused a 4-fold increase in the total mass of mammals. This increased biological production facilitated by enhanced nitrification through, for example, use of artificial fertilizers. Remarkably, we've engineered the biomass of mammals such that about 1/3 is now we humans and 2/3 is livestock such as pigs and cows, leaving only about 4% for wild mammals. An extreme example of modification of the morphology of domesticated species is that of the broiler chicken. There has been an up to 5-fold increase in body mass since the mid-20th century, and significant increase in the dimensions of leg bones will leave a distinctive fossil in the Anthropocene, representing a rapid human-forced evolution. Furthermore, the global biomass of such domesticated poultry, which is some 110 million tons, is about 3-fold higher than that for all wild birds. Some incorrectly conflate the Anthropocene and climate change, though certainly the latter is relevant to the Anthropocene narrative. Following rapid warming during the Pleistocene-Holocene transition at the end of the last ice age, since peak Holocene temperatures there has been some 7,000 years of cooling trend, which would be expected to continue ultimately into the next ice age. Human-driven modification of the chemistry of the atmosphere has reversed that trend, with global mean temperatures now rising more than 2 orders of magnitude faster than at the Pleistocene-Holocene transition. The planet is now at its warmest for 125,000 years. The upturn started in the mid-19th century, but has progressed significantly since 1975, lagging many of the other markers that I've discussed so far by a couple of decades. The driver for this climatic change has been the great acceleration around 1950 in energy consumption, in particular with increased production of oil and natural gas, which parallels the increase in global population. We're using about 80 to 90 times more energy in 2010 than in 1800. energy use since 1950 is 1.6 times greater than in all previous human history. Ice core records preserving former atmospheric compositions are used to argue that the Anthropocene is justified at series level by the magnitude of shift and rate of change associated with its onset, far exceeding that for the start of the Holocene series for numerous parameters, including, in the top panel, by significant shifts in the greenhouse gas carbon dioxide, shown in black, which is now 146% of Holocene levels and at the highest concentrations in the last 3 million years. Methane, shown in green, is an even more potent greenhouse gas. It is now 257% of Holocene levels and the highest for at least 800,000 years. In the lower panel, reactive nitrogen, here shown by nitrous oxide, shown in black, is 167% of maximum Holocene levels and perhaps the highest level in 2.5 billion years. Focusing on the markers that can potentially characterize the mid-20th century onset of the Anthropocene, it is true that many of the parameters relating to burning fossil fuels show gradual changes from the 1850s, but there are more marked inflections in the 1950s, such as, in the upper panel, rising atmospheric carbon dioxide, shown as the black curve, and methane, shown in green, and complementary fall in delta carbon-13 to more negative values, shown in orange. Similarly, in the lower panel, nitrous oxide, as with other reactive nitrogen components, shows a 1950s upturn, that's the black curve, but there's even more pronounced a change in the abundance of spherical carbonaceous particles, it's a type of industrial fly ash, which is produced from high temperature burning of coal and fuel oil, which is shown as the pink curve. Given this widespread physical, biological and geochemical evidence for a significant change to the Earth system during the mid-20th century, how can we fix the onset of the Anthropocene to a specific year? Potentially the most widespread and globally synchronous event is the fallout associated with nuclear weapons testing. The nuclear Anthropocene arguably dawned on July 16, 1945, with the first detonation of a nuclear device, the Trinity test, at Alamogordo in New Mexico. A total of 2,053 tests were carried out between 1945 and 1998, but in the context of the Anthropocene, we are interested in the 543 atmospheric tests with a total yield of 440 million tons TNT equivalent, as these are the ones to distribute a radiogenic signal that is imprinted in geological archives. Early tests and the detonations at Hiroshima and Nagasaki, although terrifying in their destructiveness, were associated with lower yields and only local spread of nuclear fallout. It is not until 1952, with the introduction of higher yield thermonuclear devices, hydrogen bombs, that radioactive material was dispersed high into the stratosphere from where it was hemispherically or globally distributed as fallout. The period from late 1952 to the end of 1958 accounts for 40% of the total number of tests and on average a detonation every 10 days. Nuclear weapons testing moratorium in 1959 to 1960 followed a rise in public and political concern about nuclear fallout debris, particularly the common fallout product strontium-90 contaminating food sources. But it was followed by an upsurge in thermonuclear tests. In 1962, the year I was born, the yield equivalent of 170 million tons of TNT, a third of the total for atmospheric tests, was detonated at a rate of 1 every 3 days. But the limited or partial test ban treaty in 1963 saw the detonations mainly go underground, creating relatively little fallout from those non-signatory nations through to 1980. Comparing the timing of two radiogenic signatures, excess carbon-14, shown in green, and plutonium-239 and 240, shown in blue, relative to the aggregate yields, shows that fallout signal onset has a time lag of about 6 months for plutonium and 2 years for carbon-14, with the radiocarbon peak lagging and at a reduced level in the southern hemisphere compared with the northern hemisphere. Carbon-14 is a commonly occurring natural radioisotope, and the atmospheric fallout in effect doubles the amount of radiocarbon in the atmosphere in the peak year of 1964, but increasing the large natural reservoir takes longer than for plutonium, which is extremely rare in nature. So with the initiation of a program of high-yield thermonuclear testing, beginning with the 10.4 megaton IVMIC test at Enewetak Atoll in the Pacific Ocean on November 1, 1952, nuclear fallout shifted from being a regional to effectively a global fingerprint of the atomic age. This more closely aligns with the significant geological markers that I've discussed previously that show shifts in the mid-20th century. The specific fallout products released following nuclear detonations depend on the characteristics of the device detonated and the nature of the detonation. Tritium, cesium-137 and strontium-90 may have high initial inventories from fallout, However, their half-lives are so short that already more than 70% of this inventory has decayed, so it will not present long-term geological signatures. Technetium-99 and iodine-129 have much longer half-lives, but as for other radionuclides shown here, they are very soluble and have very low reactivities, and therefore, rather than binding to particles, they tend to be mobile, so tend not to form good fixed markers in geological archives. Carbon-14 has a long half-life and already has importance in radiometric dating, but has natural as well as anthropogenic sources, and though it is readily incorporated into organic carbon in plants, bones and shells, disadvantage is that it is prone to biotic recycling. Plutonium-239 and 240 are seen as much more suitable, with long half-lives, 24 and 6,500 years respectively, with distinct rise in 1952 and peak inventories in 1963. They have low solubilities, binding readily to soil and sediment particles. While plutonium is typically immobile once deposited, it can, however, migrate in acidic peat profiles, adding anthropogenic plutonium to layers that were deposited before the period of nuclear weapons testing. Of the plutonium isotopes, plutonium-239 with a longer half-life and greater abundance is preferred. The plutonium signal will be detectable for the next 100,000 years, but then will leave a permanent geochemical spike following decay. This figure shows the distribution and aggregate yield of atmospheric tests by the major nuclear powers, pre-Ivy Mike, shown in purple, and the dominantly high-yield thermonuclear tests in red. The latter were mainly in the Pacific Proving Grounds, the Eurasian continent, the South Pacific, and to a lesser degree Australia and South Atlantic. Global fallout for strontium-90, shown as this overlay corrected for latitude, concentrates in the mid-latitude bands of each hemisphere, with much higher values in the northern hemisphere where most testing occurred. The equator is marked by low values despite testing near to this latitude in the Pacific. This is a consequence of circular atmospheric flow patterns transferring fallout towards mid-latitudes and limiting transfer of materials across hemispheres. This suggests that although the fallout signals are global, they may be most clearly seen in northern hemisphere mid-latitudes. Accidents at nuclear power facilities, particularly Chernobyl in 1986 and Fukushima in 2011, and licensed discharges from nuclear fuel reprocessing complexes such as Sellafield in the UK and Le Hague in France, have also put fission and other products into terrestrial and marine environments, as well as into the atmosphere, but total inputs from each of these sources have typically been less than 1% of that from atmospheric weapons testing. The bomb peak in carbon-14 in 1963 to 64 can be detected in most carbon reservoirs, including peat deposits, soil, coral and bone, or, as in here, in tree wood from a study in Poland. Note the close comparison of the timing of the atmospheric profile and that of the tree, as the record is primarily the stable isotopic composition of the source carbon dioxide sampled by the tree during photosynthesis. The radiocarbon signal can also be seen in speleothems or cave deposits, such as exhibited in examples from southwest France and Gibraltar. But here, in contrast to trees, transport of solutes via plants, soil and rock before reaching the cave commonly results in peak signals being variably attenuated and delayed compared with the atmospheric values. However, the onset of the signal is not greatly delayed and represents the more suitable marker than the peak. This example of a sediment profile in the saline Lake Victoria, Australia, is the kind of section that would be required should we wish to go down the route of defining a golden spike section. Importantly, there must be continuous sedimentation with no breaks, but also for sediment flux not to be too high, as this can swamp the radionuclide signature. This can be a problem in areas where erosion of soil through agricultural development and forest clearances is significant. It is also important that any section shows no reworking of sediment through resedimentation or burrowing. This core shows a recognizable rise from 1952 for plutonium, shown as the white circles, and a 1964 peak. There is a gradual tailing off of abundance, but is still above detection levels, probably through continuing reworking of sediment. The high organic carbon and clay fractions of the marine sediments in this example from the Santa Barbara Basin of California scavenge plutonium from seawater. Plutonium-239 and 240 concentrations initially rise in sediments deposited in 1945 to 49, exceeding background values in 1950 to 54 sediments and continuing to rise into the 1970s, the latest data available, with no sign of a distinct 1963 to 64 bomb spike. This perhaps reflects the slow settling of plutonium in deep water. It is estimated to settle at a rate of about 12 meters per year in the Western Pacific, or reworking of tritiginous fallout into the basin from the California coast. but when such particles are bound with marine snow or fecal pellet aggregates, they sink more quickly, at an estimated tens of meters per day in the Santa Barbara Basin, allowing rapid transmission to the seafloor. This suggests the first plutonium-239 and 240 signal above background, rather than the peak value, is the more robust marker for the Anthropocene. To avoid lag signals, localities from within shallow marine waters may be preferred, such as here in corals, which also have annual growth patterns providing a highly resolved independent chronology. The plutonium signal seen from a coral in the US Virgin Islands in the Caribbean reflects a location that is distant from atmospheric nuclear detonations. It shows clear 1959 and 1964 peaks in plutonium-239 and 240 that closely correspond to global fallout maxima. In contrast, a coral archive from Guam Island in the Northwest Pacific Ocean shows an initial rise in plutonium-239 and 240 in 1946, with activity concentrations increased by an order of magnitude and continued at low levels until 1951, reflecting fallout from locally tested low-yield nuclear devices. A marked bomb nuclide peak is evident in 1954, closely linked to that of large detonations in the local Pacific Proving Grounds. From 1961 to 1980, there was an exponential decrease of plutonium-239 and 240 activity, but despite nuclear test ban treaties, residual plutonium remains in the seawater and continues to be incorporated into coral growth laminae, such by 2000 levels were comparable to those in 1946. This shows that for hosting a potential golden spike section, choosing a coral that was distant from nuclear testing would provide a more typical global signal. Remarkably, sub-ice shelf deposits at Pine Island in West Antarctica also show a bomb-derived plutonium-239-240 signal that has been sourced via holes in the ice. The onset of the signal is consistent with the start of the Anthropocene. Peak values at around 1995 suggest a recycling of plutonium in downslope sediment plumes of a submarine topographical ridge. Current investigations of potential global boundary stratotype sections and points, GSSPs, are underway and expect to report in 2022. There are currently 11 sites covering a range of geological environments from undisturbed marine, estuarine and lake sediments, peat, coral, speleothems and ice core. In addition to analysing a broad range of signals associated with the onset of the Anthropocene, many of which I've discussed in this presentation, they will also be consistently investigating cesium and americium isotopes, a range of plutonium isotopes, and carbon-14 across the sites. One consideration will be to consider the extent of diachronaity of the onset of these signals in different parts of the world and in different settings. The sites cover 5 continents, but note that coincidentally many of the sites are mid-latitude northern hemisphere, where the fallout signals are likely to be most clearly expressed. To summarise some of the issues faced with using the fallout signal to define the Anthropocene, these include a time lag for peak bomb spike signal in deep oceans and lakes and in speleothems, up to a 10-year lag in equilibration in radiocarbon signal between the atmosphere and ocean, and a 2-year lag between hemispheres. The radiocarbon signal has a long tail, whereas plutonium commonly shows rapid decline after 1963, unless the sediments are reworked from plutonium-bearing deposits, such as seen in the Pine Island Glacier example. There is the potential mobility of plutonium in acidic and anoxic conditions, for example within some peats and lake deposits. Plutonium signal is not seen in speleothems and is in very low concentrations in Antarctic ice. And there is need also to avoid areas with proximal nuclear detonations, as evidenced in the corals near the Pacific Proving Grounds. In summary, the Earth system has departed from its Holocene state since about 1950, forcing abrupt physical, chemical and biological changes to the Earth's geological record. Fallout associated with nuclear weapons testing is not a key driver of these changes, but provides a globally synchronous marker coincident with the onset of the Anthropocene. Plutonium-239 has been suggested to provide the most reliable long-term signal commencing about 1952 following escalation of thermonuclear detonations. Work is ongoing to formalise the Anthropocene Epoch as a geological time unit and will require defining a global boundary stratotype section and point to be selected and approved. And finally, perhaps the Anthropocene marks not only the point at which humans began to steer the functioning of the Earth system itself, but also realised the capability to destroy our own civilization on a global scale. Thank you.
Thank you very much, Colin, and I want to echo some of the chats that have come through. Very interesting talks. Thank you for the efforts that both of you have put into preparing your presentations and for being here today. Colin, anything you would like to add to your presentation at this stage? Anything you would like to say?
I suppose the one thing is just to echo Hartmut's presentation before me. I was aware that you were going to be talking about Paul Crutzen's involvement with the Anthropocene, and I just want to say he has been the inspiration for the Anthropocene Working Group. He was obviously a founding member of the group. It was a sad loss earlier this year, but we've all appreciated his involvement with our research. To some extent, we've departed away from his original findings, largely because we are looking as geoscientists and trying to look at the evidence within geological strata, whereas obviously Paul came from the background of an atmospheric scientist, and saw much more the sort of late 18th century signal as being the significant aspect of this. But it's really in the mid 20th century we think that we're seeing the clearest signals within the geological strata.
Thank you. And Hartmut, anything after now, also listening to Colin, anything you would like to add or any questions you may have? You muted, Hartmut.
I have a question concerning the use of Colin's definitions.
Mm-hmm.
When we will have, and you never know what Homo sapien does, when we would have a new contamination of the global atmosphere by radioactive isotopes, we have a new marker, and they would be mixed. Have you thought about this? Because your talk was, yes, we have had it in the atmosphere, we had the tests, and now it's over. What would happen if India and Pakistan go into a nuclear exchange?
Mm-hmm. I suppose the important thing here is we're using the radiogenic signal as a marker, and clearly there's this significant upturn that happened in the early 1950s. That coincides with much more than just the nuclear testing. So the Anthropocene to us is not just that marker, it's all these other changes that humans have caused. So I suppose the key thing is to say, yes, there will be subsequent signals. There has been already subsequent signals of things like Chernobyl and Fukushima have caused signals which are preserved in strata. A nuclear proliferation would cause a further signal. I suppose the key thing would be what the impact on human civilization is. That would be the thing that would most radically change the Earth system as a whole. And you could then argue that we're in a new stage of the Anthropocene, or even a post-Anthropocene, in which case we have a very short duration for this epoch. But because geology doesn't work on predictions, it's not forward-looking. It's recording the evidence that's preserved in the current strata.
Thank you.
Thank you. So just a note to the participants, we're already a few minutes over, and we will probably continue for another couple of minutes, but we'll have to call this very interesting session to an end very soon. There's this a question that I think is a bit of a follow-up here to Colin. So the lead signal is not just limited to 1960. Sorry, plutonium. The plutonium signal is not just limited to the 1963 release, but also fine structures can be observed in some special cases. For instance, different explosions from 1955 to 1980. So there's really going to be a mixture of signals that will become visible.
Mm-hmm. Well, this is obviously what I was saying in my presentation, that that there is this initial plutonium signal coming in from 1945, peaking in 1963. But what we have to do is decide as to whether we take the onset of the signal or the peak of the signal to use as our primary guide for recognizing the Anthropocene in different successions in different parts of the world. And our preference, as I was discussing, is not to use the peak signal in 1963, 64, because in certain situations you can have a delay to that signal, particularly if you have, say, accumulation of plutonium in deep marine successions, where it takes some time for that to settle through the water column, or even within cave deposits, where it takes time to go through the rock succession to get to the speleothems. Whereas the onset of the signal, around about 1952, that's the global distribution of plutonium from the thermonuclear devices. It's the onset that tends to be more consistent, and also, as it happens, also the one that's closest to many of the other signals we've been looking at, the other proxies, which are around about 1950. So it's that we tend to focus upon as being the key aspect of the bomb spike. It's the start of it, not the peak.
Yeah. So I think to then unfortunately wrap up this this session, a question that I would like both of you to maybe have a brief response from one of the participants. What is your vision about the post-Anthropocene epoch? Because this will probably come a lot sooner than in typical geological timescales. So we start this time with Hartmut, and then Colin, you can finish off. Hartmut, did you hear that one?
Yes, I did not fully understand what you are asking me.
I think
Excuse me.
just your view on what will come after the Anthropocene epoch. It will come sooner than what we normally see in typical geological times. So is the Weltpolitik, if Weltpolitik is successful, this may come sooner. So what is your view? What will come after the Anthropocene?
This is an extremely difficult question you are posing, because since we have the atomic bombs, we are able to destroy what we have built up within a few days. That's why we in Germany call it what we need, Weltinnenpolitik, which means we all have to arrange for international law. And the international law has to be obeyed. And or global governance in English. And this is the main challenge we have, to cooperate. I will go back a bit concerning Homo sapiens. Homo sapiens is known to be aggressive. Homo sapiens can also cooperate. And if we shift a bit from aggression to cooperation, we will have more international law. And it started in the late 18th century when the philosophers said, instead of starting a war whenever we have a problem with the neighboring country, we should think about eternal peace, ewiger Frieden, by Immanuel Kant. And now we have a situation where we have international law and sometimes even expressive enemies sign the same treaty. And as long as we do have these multilateral agreements, the Anthropocene will last longer. But if we don't have it, it may be very short. And I think this is not obvious to many of us, that this shift from aggression to more cooperation is a key element of global governance. And we do not have major progress in the recent years. We have the European Union as one of the good signs that you can cooperate, but at the same time, we have a European Union which is suppressing a large activity in Africa. We protect ourselves by not allowing the Africans to have their market produce goods for us in large quantities. So it is a very difficult question you are posing. And it is a key question for humankind, I would say. And I like now that you have posed it, and I can express what my view is. And I was, as a scientist, over decades working on getting the message to the ordinary people and then to the politicians. Because if you do not have the support of a majority of the population, then there will be no major political decisions. But we scientists have to tell, and it was done by our two presentations, what we know and what we have found, and what the consequences are of our findings. And if we just publish in Nature or in Science or in Theoretical and Applied Climatology, to name the paper where I was chief editor, this is not sufficient. It does not suffice. We need to go public. And when I express a political opinion, I have always to tell to the listeners, this is not the scientist Russell speaking now, it is a citizen speaking, because I have a political view as well. But I must distinguish between what I have found as a scientist and what I would do, would I be a politician. And I have made this, especially in Germany, but also as director of the World Climate Research Program on global scale, getting better knowledge and expressing it in the public. And fortunately, we have the Intergovernmental Panel on Climate Change, which is the most intense way of collecting knowledge and expressing it with error bars to the world public. There is no single issue of research which is under such scrutiny like global climate change by humans. Unfortunately, we had scientists in the mid-80s to ask WMO to set up such a group. Now we have it for, since a few years only, for biodiversity assessments, and we need it for some other gaps of knowledge in the public. to bring what we have found as scientists not only to the public, but also to the politicians. And as I said at the end of my presentation, Paul Crutzen was a lucky man when he saw that the strengthening of the Montreal Protocol, step by step, through new knowledge from scientists, made us getting rid of the threat of a diminished ozone layer. And now we have to talk to all farmers worldwide that in the long term, if we continue to fertilize with nitrogen compounds as we do at present, then we will have a further massive attack to the ozone layer in the stratosphere. And so the reduction of our activities, wise reduction of our activities and keeping 10 billions well-nourished, this is the real challenge we have. And I have to stop here, otherwise I continue as I'm typically doing during public presentations.
Excellent, Hartmut. Yes, unfortunately, it is time to wrap up. I want to turn to Colin. Colin, you have a minute or so to reflect on this?
I suppose in summary, thanks to the work of people like Paul Crutzen, we have a greater cognizance of our impact on the planet. And as a result, we can almost geoengineer our future history. And we have the choice of deciding where we go with climate, with pollution signals, with biodiversity changes. And so we can try and control to some extent our future. And so that may well persist in an Anthropocene world. I guess the significant long-term change is when we transition into the next ice age. We've already delayed that probably by about 50,000 years. Potentially, if we keep going as a species, we can carry on manipulating the planet in this Anthropocene world to try and delay even further that significant change. So it's very hard to look forward as to what our future impacts will be, but you can't help but think it's one where we, as a dominant species, will try to manipulate the planet to keep it essentially the way it is.
Thank you very much. I want to thank both of you, Colin, Hartmut, for excellent presentations. I think what stood out here, in particular in the last exchange, is the importance of science diplomacy. We know we are also at this time during S&T celebrating the 25 years since the CTBTO opened for signature. The importance is very clear. It's been very successful. It's part of the global governance that I think we require, and of course it is not yet entered into force, and it's time that part of the many voices of the importance of looking after our world, looking after the environment, that we add this in one basket to say we also need for this treaty to become international law, get into force. To thank
How
you.
many signatures are lacking?
Sorry?
How many signatures are lacking?
Signatures, I think it's 4 that we require now to, no, not signatures, 3 signatures and more ratifications. So so it's, you know, it's what they always say, the first 90% is always the easy part. It's the last few percent that will make the difference, and that's what we need to do. So so thank you very much to you two for the contributions. I want to thank our technical support people here. They have gone quite considerably over their time now. Thank you, Martin, for helping here with the notes, and enjoy the rest of Friday. Thank you.
Thank you. Bye.